Hi, my name is Andrew Dowdy, and in this video lab, I'm going to be discussing an object moving at constant velocity. The first relevant principles we need to understand to observe and model an object at constant velocity are Newton's first and second laws. Because an object at rest, or not at rest, in constant motion, its acceleration should be zero, and it should be moving in a straight line. And Newton tells us that it must therefore not be acted upon by an unbalanced force, and the net force needs to be zero. So what relevant equations do I think there are to this? So I think the main equations and concepts we need to understand are friction and air resistance. I think those are going to be the chief culprits for unbalanced forces. So for my constant velocity, I tried to roll a ball across a roll of tape across a desk, and make sure that it was at roughly constant velocity. So obviously I recorded that, and you see it here, and I put it in Tracker. I set my rough center of masses and my yardstick. I checked that my frame rate was accurate, and I got this graph. And before I export the data from this graph to Excel and show you what happened there, I want to show you my glowscript model that I produced to try and approximate. So the main things I changed from the sample code were obviously the position vector. I made sure it was zero. I made sure that my velocity vector was equal to the average velocity in Tracker. Now, if Tracker was right, if I was right that this tape is at roughly constant velocity, then the average velocity from Tracker should be equal to my velocity throughout. I made sure my delta t was my frame rate so that it would be easier to do in Excel. And then I obviously ran this. I took my data, and since I know that my time steps are equal to I made sure my time steps were equal to the time steps from Tracker. This was very easy to plot. I got this graph, so let's zoom that in. So this is what we get, and as you can see, it's a pretty good. They're pretty close. So our line from glowscript is pretty close to our line from Tracker. We're very near a constant velocity. Now, or at least it would appear so from our motion graph. Now, when we move to a velocity that starts to deteriorate, and I think you see fluctuations here, but these are not huge fluctuations in velocity. I mean, they're not ideal, but they're not huge. Now, so what do I think of this experiment? So if we flipped our plus x and our xy, I don't think that would actually change much. I think it would change. It would make the appearance from friction and the constant velocity look a bit stranger, because we'd be like, why is friction accelerating us instead of decelerating us? But I don't think it would actually change much. The question that they've thought a lot about, though, is well, what's my force equation look like? And I think here, as I mentioned, this is a very smooth roll of tape. I have quite a smooth desk, quite a light roll of tape, and it wasn't moving very fast. I think that's what's relevant here. That's how I was able to get so close to constant velocity. Because if we look at our equations for friction and for air resistance, friction is our coefficient of friction, our contact force, and air resistance. The main thing we can change here is velocity. And as I said, lower velocity on the tape, coefficient of friction would be lower because we made sure to use a smooth object and a smooth surface. And contact force should be pretty low here because it's quite a light roll of tape, meaning the contact force required for the table to keep it there should be pretty low. So all in all, that's how I was able to achieve near constant velocity, was through a combination of reducing friction and reducing air resistance. And I think it was a pretty successful experiment because this graph looks pretty good. Thank you for watching.